According to the Big Bang Theory, the universe at the beginning was very hot and very small, and since then it has been expanding and cooling down. In the most common models, the universe was filled homogeneously and isotropically with a very high energy density and huge temperatures and pressures, and was very rapidly expanding and cooling. The period from 0 to 10 to the minus 43rd seconds into the expansion, the Planck epoch, was a phase in which the four fundamental forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, and the gravitational force, were unified as one. In this stage, the universe was only about 10 to the minus 35th meters wide and consequently had a temperature of approximately 10 to the 32nd degrees Celsius. The Planck epoch was succeeded by the Grand Unification epoch beginning at 10 to the minus 43rd seconds, where gravitation separated from the other forces as the universe's temperature fell. At a time around 10 to the minus 35th seconds, the electroweak epoch begins when the strong nuclear force separates from the other forces, with only the electromagnetic force and weak nuclear force remaining unified. The universe continued to decrease in density and fall in temperature, hence the typical energy of each particle was decreasing. Symmetry breaking phase transitions put the fundamental forces of physics and the parameters of elementary particles into their present form, with the electromagnetic force and weak nuclear force separating at about 10 to the minus 12th seconds. At about 10 to the minus 6th seconds, quarks and gluons combine to form baryons such as protons and neutrons. The small excess of quarks over antiquarks led to a small excess of baryons over antibaryons. It is not yet understood why the universe has more matter than antimatter. It is generally assumed that when the universe was young and very hot it was in statistical equilibrium and contained equal numbers of baryons and antibaryons. However, observations suggest that the universe, including its most distant parts, is made almost entirely of matter. A process called baryogenesis was hypothesized to account for the asymmetry. For baryogenesis to occur, the Sakharov conditions must be satisfied. These require that baryon number is not conserved, that C symmetry and CP symmetry are violated, and that the universe depart from thermodynamic equilibrium. All these conditions occur in the Standard Model, but the effects are not strong enough to explain the present baryon asymmetry.